Hi everyone, today we're going to have a quick lesson on transformers. Some of the top causes of transformer failure from my own experience and from industry data from CGRE, the International Council on Large Electrical Systems, and ways in which we mitigate them. But first, a quick lesson on high voltage transformers so we can understand how they work and some of the components involved. Basic transformer theory. High voltage transformers in the UK that operate at 132, 275 and 400 kV, which are the transmission voltages, are called supergrid transformers, or SGTs. Transformers are devices used for changing voltage because higher voltages are more efficient at being transmitted longer distances. Because higher voltages are more efficient at being transported longer distances because of Ohm's law. Increasing the voltage means a decrease in current, meaning we can have thinner conductors in our cables and overhead lines. And a lower current means less losses to heat, because of a principle called Joule's heating, which is I squared R, meaning an increase in current is an exponential increase in losses due to heat. So decreasing current is very important among many other reasons. So the basics on how a transformer works are we have two coils of wire or windings. One is the primary where you put voltage in, and the secondary is where we get voltage out. The amount of turns on each winding dictate the voltage we get out, and we define this as a ratio. The primary and secondary windings aren't actually touching, and the power flows from one to the other through electromagnetic induction, or Faraday's law, and it's the basis of how all motors, generators and transformers work. So for simple maths, if we had a transformer with a primary winding with 10 turns, and a secondary winding with 100 turns, and we put a voltage of 230 volts through the primary, we have a ratio of 10, so we multiply our primary voltage by 10, to get the secondary voltage of 2300 volts. This is known as a step-up transformer. If the secondary had a lower amount of turns than the primary, less voltage will be induced than the primary is putting out, so it will step down the voltage to a lower number. For example, 100 turns on the primary and 10 turns on the secondary will change the voltage from 230 volts to 23 volts. There are transformers that have a single common winding known as auto transformers, but these are typically used where the voltage step is small and isolation isn't necessary. However, at large voltage steps, like 400 or 275 kV to 132 or 66 kV, two-winding transformers are more common. In addition to windings, transformers also have a core made from silicon steel, which is steel made in laminated layers placed between each sheet, which helps to minimize energy loss and improve efficiency by reducing eddy currents, which are circulating currents within the transformer. The core itself helps channel the magnetic flux created by the transformer windings, further reducing losses. We'll have a future more in-depth video on transformer theory, but for now we know what a winding and a core is. So if a transformer has these really high voltage windings right beside each other, and beside a steel core which is also conductive, how do we prevent it from creating an arc and blowing itself up? For that we need an insulator. And the most abundantly used insulator used in transformers and other substation equipment is oil. Specifically selected for having a high insulation rating or dielectric strength, we fill transformers with oil, and we also wrap the windings in electrically insulating cellulose paper, which gets impregnated by the oil to help extend its life. Now let's take a look at transformer components and what they look like. So transformers are really just giant oil tanks, with the windings and core hidden inside. The first thing you'll probably notice when looking at a transformer are the pointy things sticking out the top. These are known as bushings, and have a conductive centre leading down to the winding of each phase, and an insulator outer, to give it the required clearance from anything conductive like the transformer's outer shell. Bushings are also filled with oil to increase their insulating properties, but this means moisture ingress will cause bushing failure if not corrected. More on that later. Bushings are sometimes mounted directly to the top of the transformer, but when more clearance is needed, like in a 400 kV transformer, they're sometimes mounted to a turret, which lets them be angled or separated further. The high voltage side of a transformer usually has a higher and thinner bushing, whereas the LV side usually has a smaller and wider one for the higher currents and lower voltage. Depending on the transformer, you might find an additional set of smaller bushings on one side, known as the tertiary bushings. This connects to the tertiary winding and can be used to power an auxiliary transformer, connected to earth as a neutral point, or used for voltage regulation. We've mentioned a tank, which is the biggest and simplest part of a transformer, essentially a large tank holding all the insulating oil, with the windings and core inside. After that, you may notice a little tank high above the transformer. This is known as the conservator, and is essentially an oil reservoir that allows the oil to expand and contract as it heats and cools, without rupturing the transformer's main tank. Speaking of oil heating, most transformers have large radiator banks attached, which allow the oil to move through them and radiate their heat away to the ambient air. When we talk about transformer cooling, this is where the acronyms come in. AN means oil natural, air natural, whereas OF would mean oil forced, or that there are pumps to circulate the oil, and AF would mean air forced, meaning there are fans to help assist the cooling of the transformer. Transformer cooling will be specified based on the load the transformer serves, and high load transformers will nearly always have pumps and fans to reach their full potential. Therefore, if a transformer has faulty fans or pumps, it will often be derated, sometimes up to 50%, meaning it can only handle half of its nameplate rating. The pumps and fans don't run continuously and will switch on depending on the temperature of the oil. The oil temperature is detected by the Oil Temperature Indicator, or OTI, which continuously monitors the temperature of the oil. Similarly, a WTI, or Winding Temperature Indicator, checks the HV and LV windings for over temperature, which might indicate a fault and cause an alarm or trip the transformer off the network. Other components you might not easily see include pressure release devices, or PRDs, which release gas or oil if the tank starts to pressurize and risk rupturing. This release is directed safely to the ground into the transformer bund which contains any oil leaks. Another monitoring device is the Dissolved Gas Analysis Device, or DGA, and isn't fitted to all transformers but is common on newer ones, and is used to periodically measure the oil for dissolved gases, which can indicate a fault depending on the gases produced. Since the transformer oil is a hydrocarbon, most of the byproducts of its decomposition are flammable gases, like hydrogen, methane, ethane and acetylene. Gases like carbon monoxide or dioxide indicate that the cellulose insulation is breaking down, and detecting oxygen, nitrogen or moisture indicate a transformer leak, allowing ingress. Low energy faults result in hydrogen, methane and ethane, whereas acetylene forms from high energy arcing, meaning a major problem. To help remove moisture from the transformer oil, we use breathers, which are non-silica desiccant, which absorb moisture from the air entering the conservator as it breathes due to the expansion and contraction of the oil. Dry cool devices help remove moisture from the oil and paper insulation over time, like a continuous dehydrator, maintaining the insulating properties of the oil. If gases are produced in the oil, then the Bucholtz relay located high up in the transformer in the pipework to the conservator tank will detect a rush of gas, quickly displacing the floats inside, and will trigger the protection to trip the transformer. A slow accumulation of gas over time will also trip the Bucholtz, and the sight glass on the side allows engineers to measure the accumulation of gas. The relay is also fitted with a metal flap, which will trip if a large rush of oil is sensed, due to the rapid heating of the oil rising to the conservator tank. That just about covers the components on the transformer. You'll often have a local control cubicle, or LCC, attached to the transformer, or right beside it, and this connects things like the fan controls and the current transformers from inside the transformer to the rest of the substation for power and control. The transformer might have a noise enclosure around it to help reduce the humming sound it makes from bothering its neighbours or the wildlife, and the transformer also sits in a bund, which is a concrete structure designed to contain oil leaks. If two transformers are right beside each other, there might be a fire deluge system in place to minimise the spread of fire if one were to happen if the tank ruptures, and if not, then a blast wall is typically built from brick, concrete or metals to reduce the spread of fire if a fault occurs. So now you know all the basics about transformers. How do they break? Insulation breakdown. So we've established that transformers are filled with thousands, if not hundreds of thousands of litres of oil. The oil is also the insulating medium between the high voltage parts, preventing short circuits inside. Transformers also use cellulose insulating paper around their internal windings, which is impregnated by this oil to prevent it from degrading. Degradation can occur over time through factors like heat, moisture and electrical stress, which can make the paper brittle and speed up its degradation. At a certain point, this breakdown of the paper insulation can lead to a loss of dielectric strength, or put plainly, the insulation between the two windings starts to fail, causing a short circuit or arcing, increasing the heating and chance of fire. This arcing also causes a breakdown of the oil inside the transformer, which is hydrocarbon and gives off flammable gases, depending on the breakdown type, including hydrogen, methane and acetylene. Dissolved gas analysis usually happens in intervals of anywhere from 15 minutes to hourly or more, and isn't fitted to every transformer, especially older ones where an oil sample is taken usually by bottle and sent off to a lab for analysis. So to help protect the transformer even without DGA, we rely on the Bucholtz relay, WTIs and OTIs as described earlier. Transformer oil needs to be regularly reprocessed to remove moisture and contaminants, which can reduce its insulating properties. However, in older transformers, this regular reprocessing might mask faults over time, so interpreting the oil test results is super important for your supergrid. Bushing failure is the next common failure for a transformer and fails in much the same ways as the insulation breakdown, since they're also filled with oil, such as by water ingress, internal degradation, partial discharge and thermal runaway. Winding failure is another form of failure in which short circuits can occur, leading to inter-turn faults, or complete failure, and are also caused by thermal aging, mechanical stress from through faults, and poor manufacturing, which can lead to transformers failing in the first few years of operation, rather than 30 to 50 years later. Another component fitted to transformers that can cause a failure is the tap changer, which allows the transformer to change the voltage it outputs to respond to changing demands on the network. Transformers, as we've discussed, have windings, and taps are different points on that winding that vary the output voltage. To change the tap, a mechanical drive physically moves the tap, diverting the load through a diverter, which can take the load momentarily while the contacts move, reducing the internal arcing that occurs as the contacts are made on the tap. A fault on the tap changer could result in too much arcing, vaporizing its oil and igniting the gas, causing the tank to rupture. Other factors that can cause a transformer fire can include surges, such as from lightning strikes. However, surge arresters and arcing gaps are used to mitigate this, as well as potential issues with cooling fans and oil pumps. However, this would usually cause its own alarm, and the transformer would be taken out of service long before a fire could start. A final factor could be incorrectly set or failed protection relays, which don't act in time to remove the transformer from service, or failed switchgear, such as a circuit breaker that would disconnect the transformer from the network. However, this is usually planned for, and if the first circuit breaker fails, one further back will act as the backup and still take the transformer off network, and likewise backup protection will act if main protection fails. Transformers are some of the most expensive assets that can take years to procure and months to install and commission, so we do everything we can to protect them. Summary: I hope this video was informative and educational, and I'll be producing more videos in the future on all things industrial history and electrical theory, explaining how different components of a substation work and commenting on past, current and future projects in the UK. Thanks for watching, and make sure to share this video to help inform others, and subscribe for more electrical content. And if you're interested in a career in maintaining and designing these critical important assets, there's an industry-wide shortage of engineers in the UK, so look online for careers and apprenticeships with your local transmission operator, distribution network operator, or in the supply chain. Take care.